A Portland Community College Mathematics Telecourse. A course in arithmetic review, produced at Portland Community College. These next few lessons are going to review some simple properties of basic geometry. For instance, this tape, the idea of perimeter and circumference. To begin with, the word perimeter really simply means the distance around an enclosed figure, usually a straight lined figure, but it could be curvilinear too. Now our second word, circumference. What is the circumference around the circle? Usually it's stated what is the circumference of the circle, but around certainly conveys its definition. The circumference is to a circle what perimeter was to the last figure. It simply is the distance around the circle. So our vocabulary, the two simple words, perimeter and circumference, each of which mean distance around a closed-in figure, with circumference sort of being restricted to the distance around a circle. A few simple problems, but we want to use this as a vehicle to move you into a comfortable feel with formulas. What is the perimeter around a rectangular field? We have a field, rectangular. It's 820 feet by 300 feet. Well, it doesn't take too much imagination to realize I've got to double this to get this side and double this to get this side and add them together, or in short, that plus that plus that plus that. And we'd get this, which worked out gives us 2,200 feet. But we want to concentrate on what we have. Really, we said take 2 times the length and add to that 2 times the width. Let's say that more formally. First, what is a rectangle? It's a 4-sided figure in which the opposite sides are not only equal, but they're perpendicular. That is, they form right angles. And in geometric statements, since usually we sketch and sometimes it's a bit sloppy, we use this little mark right here to indicate that our 2 sides are perpendicular. So if you see a geometric figure with a little square in the corner, that's simply a shorthand notation to say right angle, which is the same thing as saying there is 90 degrees of measure there. Now this rectangle has a length and it has a width. And to find the perimeter, we simply took 2 of these and added to 2 of those. So let's state that in pure symbols. Symbolic perimeter is 2 times length added to 2 times the width. Or we could have said, let's add the length and width first and then double the sum, and we get the same results. Now this way of writing something we have traditionally called a formula, which is nothing more than a convenient way for us to communicate what we already know to somebody else who perhaps does not know it. We have to tell them what the letters stand for, but then the formula tells you how they are related mathematically. Another one, what is the perimeter of a square with a side of 22 centimeters? Now what is a square? It is simply a rectangle in which all the sides are equal. So rather than taking this plus this plus this plus this, it's easier simply to take 4 times one of them. See, we're multiplying a measurement with a pure number, and of course we would get a perimeter of 88 centimeters. Let's state that fact by formula. First, a square is a rectangle with 4 equal sides. So we could call them all S. Some will call them E for edge. Some will call it X for unknown. And the perimeter is simply 4 times the length of a side. Or if you were using E, 4 times the length of an edge. The choice of the letter is an arbitrary one. It's up to you. But again, catch the idea of using a formula to communicate something very briefly and very succinctly. Of course, the real world doesn't act that simply. Even in drafting, such a figure as this would be considered super simple. So at that point, we simply recall that the word perimeter simply means distance around. So in this case, piece by piece, let's simply begin to add it. This side plus this side. Now it gets a bit tricky. It seems as though they didn't tell us much else, but they did tell me this length is 2.5 meters, and we can see by projecting it over that this much of this side would be the same thing. So that plus that is 5 meters, so I'll add that on, and we have it here. But what about the rest of it? They don't tell us anything. Well, here we have to use some common sense. Notice if I take this plus this plus this, that to go there, then there, then there, I have simply gone this length right here, so that gives me another 56 meters. So sometimes you have to be very clever and notice those things. So we have another 56 meters. Now can you see that with what's left we can do the same kind of thinking? Notice that this piece down to here and this piece down to here, that plus that plus that is equal to that. So we have another 14.3. Then when we see we have indeed covered all the directions that we can, those that we could directly, and those that we did indirectly by comparing them with things we did know, then we now have our perimeter completed. Now we simply complete the sum to find its numerical value. And we have our final perimeter of 145.6. Now the point of this is that when you have a complicated figure, sketch it, then with a heavier pencil or colored pencil begin to run over those areas you know, and then begin to ask of those that you don't know directly, how are they related to what you do know? Then in bits and pieces simply accumulate every side to that perimeter. And of course sometimes they give you every side, so you just recall perimeter simply means add up all the sides. And we have the sum 25.3 centimeters. Notice that indeed we are adding like measurements, which a previous lesson said we needed. Now, while we're at it, let's define some special triangles very quickly. A right triangle is a triangle that has one angle in which two sides called legs are at right angles. That is, they're perpendicular to each other or 90 degrees. And generally, the side across from that right angle is called the hypotenuse. By the way, that's spelled exactly as it's pronounced, hy-pa-ten-use. Okay, so a right triangle is a triangle with a right angle, or two perpendicular sides. A triangle with two sides equal is called an isosceles triangle. A triangle in which all three sides are equal is called an equilateral triangle. By the way, it also happens that all of the angles are equal as well. And furthermore, they're all equal to 60 degrees each. Now, in an isosceles triangle, the angles attached to the two equal sides are also equal. And the third angle can be different than those two, and usually is. Now, a triangle in which none of the three sides are equal, not even two, is referred to as a scalene triangle. Now, what about its angles, or the angles of a triangle in general? Now, it's a fact that in triangles in general, the sum of all of the angles is always equal to 180 degrees. That sometimes is an important fact to have. Now let's talk about that circumference of a circle. Recall that the distance across the circle through the center is referred to as the diameter and is usually symbolized by the letter D. Now this formula says that circumference is some number, and you might recall we pronounce this Greek symbol pi. It's a number. By some number pi called the length times the length of the diameter. Pi is a number that's approximately equal to 3.1416. It goes on forever. It is not a fraction. We'll talk about that more later. But you can find the length of the circumference by simply measuring the length of the diameter, then multiplying times pi, and since it is an unending decimal, round off to as much accuracy as you need. Now the distance from the center of the circle to the edge we call the radius, and usually we symbolize it by the letter r. Now notice the radius is really half the diameter, or you could say 2 radiuses is equal to the diameter. See, diameter is 2 times radius. So we could replace this d by what it's equal to, 2r, and we would get that the circumference is also found by doubling the value of pi, and that times the value of the radius. So these two formulas are just two forms to get at the same thing, the circumference. Now where did that value for pi come from? If you were to take a circle and measure its circumference, I'll call it circumference 1, and divide it by its diameter, I'll call its diameter 1, then measure the circumference of another circle, I'll call that circumference 2, and divide it by the value of its diameter, I'll call that diameter 2, and do that to any circle you could draw. Take its circumference, divide by its diameter. It would turn out that this ratio in every single case is equal. And whatever that ratio is experimentally, we have denoted by the Greek symbol pi. There's the value of pi out to a lot of places of accuracy. Some of you have learned that pi is 22 sevenths. That's not quite true. If I were to divide 22 by 7, I would get this. And you can see there, to the nearest whole number, they're the same. Tenth, they're the same. Hundredth, they're the same. But at the thousandth and from there on, they're different. So this is merely an approximation to pi, and it's only accurate to the nearest hundredth. So if you ever need accuracy beyond the hundredth, don't use the 22 sevenths. It's not accurate enough. Now this is a lot of place accuracy here. Some people will round it to the nearest 10,000th. Of course, since that's 5 or more, that would round that up, and I would get that. And most frequently, you have seen the approximation of pi rounded to the nearest hundredth. How much accuracy you use really depends on what you're using with the number and how much accuracy you need in your measurements. Let me give you a rather cute way of remembering this value that was given to me years ago by one of my students. A simple sentence that most of us can remember. May I have a large container of coffee? Now count the letters in each word. 3, 1, 4, 1, 5, 9, 2, 6. May I have a large container of coffee? Pi, accurate to the nearest hundredth, thousandths, 10,000ths, 100,000ths, millions, out to the nearest 10 millionths, which is more accuracy than you'll ever need for most problems. It's a nice trick, isn't it? Now let's use those facts for this problem. What is the circumference of a circle with a radius of 5.6 yards to the nearest tenth of a yard? Okay, so we want the circumference. They told us a radius, so we find the formula relating circumference to radius if we don't remember it. And it is, circumference is 2 times the value of pi times the value of the radius. Now substituting what these letters stand for, we get this, which is a pure number times a pure number, decimal, times a measurement number. So our answer will be in yards. Multiplying that, we get this, but our problem stated we wanted it rounded to the nearest tenth of a yard. So this is my tenth. This is 5 or more. So I round up and get 35.2 yards is the circumference of that particular circle. Usually in surveying, architecture, or drafting, our geometric figures is not as simple as a simple rectangle or a circle, but combinations of them, and they give you minimal information, and with that minimal information you must determine everything else. So let's say along with this sketch we were told that these are right angles, which tells me that this much of the figure is a rectangle. And let's say we were also told that this end is a half circle. Now, do you know the name for half circle? It is semicircle, or if you would, a half circle. From this, can we see our strategy for determining the perimeter? Well, if this is a rectangle, we can see that this side will be equal to this side, so we know that even though they didn't tell us. So we know that if we double this, we've got this length, that's 32. Then add this to it, we have 42 meters so far. But to that we have to add this half circle. Well, we know that the area, the perimeter of a circle is 2 times pi times the radius. We have the 2. The pi, let's use 3.142. Now the radius, apparently they don't tell us that. But remember that radius is a distance from the center to the edge of the circle, which is half of this side, which is 5. So in fact the radius is 5 meters, as a matter of fact, because we can only add like units with like units. But if we added this onto this, we would actually be adding in the circumference of an entire circle, and we want only a half circle. So we want a half of this, which using my cancellation law gets rid of that. So now all that remains for us to do is to multiply this, add on to this, and have it be made known to us how much accuracy we wish. So in this case, let's say we want the accuracy to the nearest tenth. And here you get to see order of operations, don't you? Here's a multiplication, here's an addition, and the order of operations says I do the multiplication first. So 3.142 times 5, and then add that onto 42 equals, we have 57.71, but if we desired the accuracy to the nearest tenth, that would be 57.7, and our units of measure was meters. And again, remember that if this were in feet and this were in meters, I could not perform the addition because I can't add meters to feet. I can add meters to meters or feet to feet. So in a case like that, I'd have to either here or here perform a conversion of units as we had on the last lesson, and then add those two similar units. Another point we're trying to make here is that simple rectangles or circles don't appear by themselves as a rule in architecture and drafting. There are many, many combinations of them. Let's show another problem. Here is an athletic field, and we need to know what the outer perimeter is. Of course, outer perimeter means the distance around the outside. Can we determine what's the least measurements we need in order to find that if we were told that in fact this central portion here is a rectangle, and if we also were told that the end curves are semicircles? Can you see that it's simply enough for me to know this one length? Let's say we had measured it and found it to be 120 yards. Then we need to know either the radius or the diameter of one of the end circles. Let's say we measured that and found it to be 50 yards. And again, we remind ourselves that if this is in yards, so must this, or vice versa. And we don't have to find the circumference of a circle, then have it. We make note that if I take this and then add it onto this, together they constitute a whole circle. So in effect, I need to know the circumference of one circle, or simply split and spread apart, added to this double, because being a rectangle, this will be as long as this, so their length together would be 240 yards. Then the circumference of a circle is 2 pi times the radius, or if you would, pi times the diameter, which I will add on to this piece here. So pi, let's say we need to know that to 3.142 again, times the diameter, but we know the diameter is given to us as 50. Now we do this first, then add the results onto this. This, of course, is a pure number times a measurement number, which is possible. And I'm adding like measure to like measure, so that too is possible. So the order of operations directs that I do this first, then add the results to this. And again, usually at problems of this type, you're going to do the work on the calculator. So 3.142 times 50 added to 240, and to the nearest tenth, if that's what's desired, I have 397.1 yards distance all the way around this athletic field. And once you are comfortable with geometric terminology, frequently your problem will simply be given to you verbally with no sketches or plans. In this particular problem, we know just by the use of the word perimeter that we want the distance around an enclosed figure. We know that we'll be dealing with a triangle, but specifically an equilateral triangle, which we need to remember, or if we didn't, we would look it up in a reference book, that it's a triangle in which all three sides are equal. See, lateral is a root word for side, and equi. So we have equal sides of a triangle. And they told me that one of the sides was 49.2. Well, rather than taking this number and adding it to itself again, we can see just by the arithmetic of the situation that if we simply take one side and triple it, we get the sum of all three sides. And of course, 3 times a unit of meters is still meters. And of course, many figures which are given to you seem to be incomplete in their information. But really, with a little thinking, you'll find that they aren't. First, if they want the perimeter, we can see from the obviousness of the placement of the numbers that I can add that to this, and I have 58 units of measure, whatever this is. Let's say they're meters once again. And we can see, in this case, we might have to ask for further clarification that these two are equal. Well, if I add those two, double one of these, I get another 20 meters. But it looks as though I don't know that, or that. In that case, ask, do I know what they are if I take them all together? Just as though it's one length that's been broken into segments. And of course, at this point, you would realize that that plus that plus that is once clear across, which we already know, which is another 38 meters. So the only thing that's missing now is this curve distance. So what we need to ask now is this in fact circular, and is this the center? If it is, then we know that this is a semicircle, and the circumference of a circle is pi times the diameter, and a semicircle is half of that. So I would take some convenient value of pi, depending upon how much accuracy I want, times the diameter halved. And we can see that this diameter is the same as this length, and we want it halved, which would be 10. So this would be 31.42 meters. Then we make the note that we're adding meters to meters, which is permissible. Otherwise, I'd have to do some conversion of units. So we simply add these like units of measure, and we finally have our requested perimeter. In drafting or surveying, when we draw a sketch or a more formal set of plans, it is generally the practice that you are to give a person minimal information. That is, information that they need, everything that they need, but no more, so as to not clutter the sketch or the plans. So it's left for the user of these plans to take what is given, geometric facts that he knows in order to use those plans, in order to determine everything else. This is your host, Bob Fennell. We'll see you at the next lesson.